take your time. We will make you the presenter, and then you will be able to share your screen. Okay?
Can you hear me?
Yeah.
Yes.
Hi, Gonzalo. Can you hear me?
Yes, we can hear you.
Okay, nice.
Now you are presented. You should be able to share your screen. Or you will.
Plus button.
Share the full screen, but just the tab that you like.
Let me try to share.
I will be back in 2 minutes. Okay, please make sure.
Okay. Can you see the presentation, Gonzalo?
Yes.
Nice. Try to pass here the presentation. For me, it's working. It's passing the presentation for you too?
Yes, it's working properly.
Okay, nice.
Yeah, almost there. What's the time? 1 minute. 1 minute to go. I don't need this. Okay, I don't like this. Decide. Okay. So Euclides, are you ready?
Oh yeah, should I turn on the camera?
But as you like, you want to show your face? You're welcome.
No problem. It's not so beautiful, but I think you'll not be scared.
No, you are a handsome man.
Okay, guys, nice. It's working.
No, it's okay. No, I think that the three are okay. Okay, so thank you everyone for being back to the afternoon session of this meeting. And our next speaker comes directly from Fortaleza. No, not Fortaleza. Where are you? Are you in Fortaleza or?
In Juazeiro do Norte, Cariri.
Juazeiro do Norte, no Cariri. It's a region of Brazil.
Yeah.
Show you a map. Just to locate.
Yeah, I have a map for that.
Thank you for the map. So, Euclides is a good friend of mine in Ceará, in Brazil. And he's going to tell us about Bumblebee fluctuations in curvature spacetime. Okay? Please go ahead.
Thank you all for being here. Thank you, Gonzalo, and all the organizers for inviting me for this great meeting. I think it's the second time we are together, so it's a really good chance to share our works, right? So today I'm gonna talk about Lorenz symmetry violation in curved spacetimes. We want to see how the curvature of spacetimes affects these Lorentz symmetry dynamics. Okay. In particular, we are interested in this Bumblebee field. Bumblebee, it's a self-interacting vector field which drives the Lorentz violation. So we're gonna start by defining these Bumblebee fields and see what the features of the theory, what's the problems, and what's the goods of this theory. And then we choose a specific and very symmetric space-time. We take the ADS5 space-time. It's ADS5 brane world, actually, because we also want to see what the effects of the extra dimensions on the Lorentz violation. At last, we see the fluctuations of this self-interacting field above the vacuum expectation value. Okay, so first, I'm a professor here in Brazil. Here's a map of Brazil here. So we have this northeast region of Brazil. Okay, see, here we have this Ceará, which is my state map. In the south of Ceará, we have this region here. It's called Cariri. So Cariri, it's a region. It's not a political region, but it's a region where lived the Cariri people. It's a Native American people. We live here, and this region it's very important for at least 6 states of Brazil, and we have a university here. Okay, so here is Cariri. We don't know actually what Cariri means because there is no much Native American to ask, but that's the region. Okay, so what's the Bumblebee field? So we are talking about Lorentz symmetry violation. So what is Lorentz symmetry violation? We can think of the space-time with some background vector here in space-time, this b mu, and this vector violates the symmetry, the Lorentz symmetry, because all the vectors, when you apply Lorentz transformation, all these vectors, or tensors or spinors, they vary according to Lorentz symmetry. But this background field does not. When you apply an active Lorentz transformation, this vector is a background vector. So there are many ways which this Lorentz symmetry violation can be applied or can be sourced. Okay, there is many origins for this Lorentz symmetry, and we are interested in one model, which is this Bumblebee model. What is Bumblebee model? The Bumblebee model is suppose we have a vector field, which is a self-interacting vector field. So this self-interacting vector field has a vacuum expectation value, and this vacuum expectation value of a vector field is a vector. So it defines a vacuum all over the space-time, which is this background vector which drives the Lorentz symmetry. Okay, so the theory is that this Lorentz symmetry breaking is dynamically generated. It's generated by an spontaneous symmetry breaking process. So the vacuum of the theory is this this vector of space-time. So that's the principle. So let's assume a very simple model. For example, if you consider a vector with a Maxwell-like term, this first term here in equation 2, and a potential, okay, for this vector. This Bumblebee vector is this vector here in space-time, this b mu, okay? And for this potential, we have vacuum expectation value b mu, which we can define this norm by contracting with the metric. Okay, so what's the big question? The big question is how the space-time curvature affects this spontaneous breaking of the Lorenz symmetry. In particular, we know that when we have this spontaneous breaking of symmetries, we have these Nambu-Goldstone modes, and also we have these massive or Higgs modes. So in particular, we are interested in how the space-time curvature modifies the Nambu-Goldstone modes and the massive modes. Okay? Great. So the first thing we have to do is define this vacuum here, this expectation value, a vacuum expectation value in the curved spacetime. In flat spacetime, it's easy because we can see that all these background vectors here, b mu and b mu prime, they all are parallel to each other. So we just have to assume that the derivatives of this vector is 0, okay? All of them. But when you go to curved spacetime, we have a little problem here, because now if you try to translate this vector b mu in this point to b mu prime in this curved spacetime here, we have to use not the conventional derivatives, but for example the covariant derivatives. Okay, so there is only one way here where you can see that b mu and b mu prime have the same norm. This you have to put some condition on this derivative contracted with this direction. Okay, so it might depend on direction, or it might depend on this derivative. Okay, in the literature we have some proposals. For example, Bertolami and Paramos, they proposed, for example, that the vector here is covariant, the vacuum which breaks the Lorenz symmetry is covariantly constant. Okay, that's fine. The norm of the vector is constant, so the potential is vanishes in all the space-time points, no problem. But if you okay, another good thing is that now you have to define the derivatives of the vector field all over the space-time, okay? But if you now have the derivatives of this vector, this background vector, the vacuum, so maybe the vacuum has some kind of field strength, which is not 0. But with this definition, so now your background vector has a vanishing field strength. Okay. Moreover, if you consider a geodesic, in other words, if you consider the background vector and a motion of a massive particle, this projection is constant. Okay, so these are the good things of this definition of the vacuum. But we have this curvature constraint here, because if you take the derivative once more and you take this anti-symmetrization process, so if this is also 0, so you have this constraint here where the Riemann tensor contracted with the background vector, it's 0. So it seems that there is some kind of privilege direction which also modifies the curvature in that direction. Okay, so there is a very strong constraint for the curvature. Here we want to consider another definition of the vector, we take this definition of the vector. We consider a vector, a background vector, where the norm of the vector is constant. If you take the derivative and consider this connection to be torsionless and compatible with the metric, so you end up with this constraint here. This constraint has no curvature at all, and instead of the derivative of the background vector be zero, it's actually his contraction with the vector itself, which is zero. So it's a less restringent constraint. And if you apply this second derivative once more, you end up with no constraint with the curvature, but constraint with the vector itself. Okay? So in some sense, this definition of vector, it's more wide. Okay? So you're gonna take this. Okay, so after we define the vacuum of this Bumblebee field, let's consider, for example, what happened when you consider very symmetric space or space-time. So let's consider this Randall-Sundrum model 1. In Randall-Sundrum model, we have this ADS5 space-time, we call bulk, and embedded in this space-time, we have two branes, or two main branes, are two hypersurface, okay, which has this time derivative itself in this direction. So it's a four-dimensional subspace or submanifold, okay? Let's consider it flat. So we have a flat brane here at the origin and a flat brane here at this distant L from the first brane, okay? If you consider only one extra dimension, we called Y, which is perpendicular to the branes. And if you consider that the metric of the brane itself here depends on the position Y, so we have this warp factor exponential decreasing with this extra dimension. Okay, so why this model is so interesting? Because we can relate quantities here in this brane to quantities here in this other brane, and these quantities are related by the metric, by the geometry. So if this geometry has this warp factor, so the quantities here are related to quantities here by this exponential. So Randall and Sundrum use this model to explain the hierarchy problem between the Electroweak scale and the Planck scale. So the theory goes as, in this y equals 0 brane, you have both the Planck scale and Electroweak scale at the same scale. But then, in this brane here, which is our brane, in y equals L, the Electroweak scale is modified, is suppressed by this exponential factor here. So it's a kind of geometric explanation for the hierarchy problem. So we want to see if it's possible to have some kind of hierarchy or some suppression, exponential suppression of this model, of the self-interaction model, also in Randall-Sundrum model. So we first consider here a conformal metric, okay, a conformally flat metric. So we can, using this the constant norm condition, which defines the background vector, the vacuum vector. So we can see that the vacuum vector in Randall-Sundt model can be defined as a background vector here in the flat spacetime, okay, multiplied by the warped factor of this ADS5 space. Okay, so if you assume that the bumblebee, the field itself, varies in the same way, and you replace these conditions on the potential, you end up with a four-dimensional, here it's a four-dimensional bumblebee self-interacting potential multiplied by this factor, lambda times this integral all over this exponential factor. So in each brane, if you consider the bulk, now you have this slice. So each brane is a slice. In each y, you have a brane. So you can define an effective self-coupling constant of the bumblebee, which decrease with the extra dimension. In other words, you have here a very a bigger self-coupling constant for the bumblebee model, which drives the Lorenz symmetry breaking, and it goes down, and this is in our brane. So in our brane, the self-interacting constant is suppressed by this exponential factor. So it's smaller. So this might explain why the Lorenz symmetry effects are predicted to be very small. It's because they are not so small in other brane. So in this y equals 0 brane. Okay. So, and what about the fluctuation, the Nambu-Goldstone and the massive modes? So in order to analyze how the curvature affects these modes, these fluctuations above the vacuum, we consider the equation of the motion for the bumblebee. This current here, it's actually a self-interacting current, so it depends on the bumblebee itself, okay? And it satisfies a conservation equation. So now we consider a fluctuation chi mu above the vacuum b mu, okay? And the equation of the motion for the fluctuation has, it's like the Maxwell equations in curved spacetime. This 1, 2, 3 first terms are like the Maxwell equations, but now you have the field strength for the vacuum, and you have this extra interaction here. It's a self-interaction because it depends on the self-interacting constant here, okay? So this is the fluctuation, but we can decompose this fluctuation in the modes. So if you consider that there is a background vector here, which is the vacuum, b mu, so you can decompose along the vector, along the vacuum, and perpendicular or transverse to the vector, okay? So this transverse mode here, we call a mu, and this longitudinal mode, we call beta, okay? So in flat spacetimes, when you make this decomposition and use these equations of the motion for the fluctuations, you end up with the transverse modes are massless, so they are the Nambu-Goldstone modes, and one additional massive mode, which is beta. So you can see that the Bumblebee model also offers an explanation for the photon. The photon can be seen not as an elementary particle, but rather the photon can be understood as a kind of Nambu-Goldstone mode of the Bumblebee field. Okay? So the problem is, okay, in nature, we see this Nambu-Goldstone mode. It's the photon. But we don't see this extra mode here, this massive or Higgs mode here. So what happened with it? Okay, so in curved spacetime, the longitudinal mode or the beta mode, there's a huge number of different terms. All these terms here, they vanish in flat spacetimes because you don't have the curvature, you don't have derivatives, the derivatives of the vacuum it's zero, so all these terms are zero. Only this last term here is not zero. It's actually the term which depends on lambda. And this is a massive term. So the longitudinal mode is a massive mode, and his masses comes from the Lorenz symmetry, spontaneous Lorenz symmetry breaking potential. Okay, but you can see there are many more modes here, and the transverse mode has no masses in flat spacetime. There is no mass here for a mu. There is no a mu term here. These terms here are actually just the usual Maxwell terms in curved spacetime. Okay, so we want to see how curvature affects this model, these modes. The problem is these equations are very complicated to attack in a general case. So let's assume a very specific, a very symmetric scenario. So let's assume that our brain, it's actually an Friedman Robertson Walker brain. So it's a homogeneous and isotropic brain expanding in time. Okay, so this brain, which has curvature because it's expanding, is embedded in the ADS5 space, which also has curvature. Okay, and let's assume that the vacuum is space-like, and he's pointing only on the extra dimension. So there is no component of this vacuum expectation value, this background vector, along the brain, on the brain, only in the extra dimension. If you do so, you wanna answer another question: how the modes propagate in the extra dimension and along the brain. So you have to make this Kaluza-Klein decomposition. It turns out that when you replace this in the equation of the motion, along the brain, the equation 19 says that you just have usual photon corrected by this m square. What the origin of the m square is this Kaluza-Klein masses. So the extra dimension and the curvature of the brain does not provide masses to the transverse mode, to the photon. Only the compactification provides these Kaluza-Klein masses. Okay, so there's nothing new. If you do the Kaluza-Klein decomposition for the photon in 5 dimensions, you get the same result. Okay, and let's see what happened to the another mode. the longitudinal mode, the massive mode. So the massive mode has Lorenz violating source mass here, you can see. And there's also this coupling between the transverse mode and beta. Okay? If you consider that this longitudinal mode is just evolving in time with the time evolution of the brain, with the expansion of our brain, and if you just consider the massless Kaluza-Klein mode, you have a continuum of Kaluza-Klein, a continuum tower of Kaluza-Klein modes for the photon. But if you just consider the massless one, you end up with this equation 22 for the longitudinal mode. So this equation has this dissipative term here, the second term. So if you consider that the expansion of the brain is in the de Sitter phase, so the Hubble constant is constant. So this additional mode, this massive additional mode, longitudinal mode, actually decrease with the cosmological time. So it was bigger in the past, and he went up exponentially decreased with the decreasing of time. As the cosmological expansion takes place, so it's exponentially decreased. Okay? So if you assume that, for example, this Lorenz symmetry breaking process, which is spontaneous, it's an spontaneous breaking of some symmetry. If you assume that this spontaneously breaking is occurring during, for example, the early universe, we know that happened some breaking of another symmetries in the universe. If you consider, for example, that the mass of this additional mode is in the same order of, for example, during the inflation, so we can see here that, let me go back. So you can see that this additional mode is suppressed in time by the expansion, by the inflation. And so after the inflation, you almost have nothing of this, no more this beta mode. Okay. So the main result here is that if you consider very general space-time, it's very difficult for you to answer the question. Can we see these modes, these excitations? Can we see this happen? And can we split these excitations in Nambu-Goldstone modes and Higgs modes? This is very difficult to do here in this vector model. But if you consider a very specific or symmetric spacetimes, it's actually not so hard. It's easy to see that you have these two modes, they decouple, and the photon or the Nambu-Goldstone mode evolves in time just as a photon, and the additional mode, the longitudinal mode, decays with time. So it might explain why today we don't see any of evidence of these modes. Okay, we are seeing back in time this. We are considering that this breaking of the Lorenz symmetry is occurring during the early universe. So there's a lot of perspective to do, right? Because we didn't consider, for example, the coupling between the Bumblebee and fermions, for example, to see how this breaking of symmetry can also breaks other fermion symmetry. And we didn't see, for example, what's the back reaction of this Lorenz symmetry process, the Nambu-Goldstone and the massive terms, the massive modes, on the gravitational field itself. So this is something we are just working on, okay? So I'd like to thank you all for listening to me and all these collaborators and all the organizers for inviting me. Thank you.
Okay, we have time for questions.
There is one on the chat.
Yes, Albert, do you want to ask or? Well, I don't know, Albert, if it's.
Albert, can you open your microphone? Want to ask? Well, we can read.
Yes.
So Albert Petrov is asking if it is correct to speak about photons in our theory is not gauge right.
Okay, let me see if I understood the question. Well, this is in a specific model, right? So you could also consider, for example, that you already has some kind of Lorentz symmetry breaking process, a different process, okay? And you have the photon. And this photon Lagrangian is modified by this background vector which you defined, okay? So in this sense, the photon is an elementary particle which is modified by the presence of this background vector, okay? This is totally possible, okay? You can consider this model. There are models like this. And what you are considering this in this particular model, in the Bumblebee, is that there is no photon at all. The photon is not an elementary particle, but rather it's a Nambu-Goldstone mode. Okay. So these are different models. Okay. And how can you consider a photon in a Lorentz violating theory in the first place? I mean, the photon, it's a vector representation of the Lorentzian group, right? So does it make any sense? Yes, it does, because we are not breaking the Lorentz symmetry in the observer transformations. So you can continually have some transformations between observers, in other sense, only changing the coordinates of space-time, okay? And this is kept constant, okay, in the Lorentz symmetry breaking process. What you are actually breaking is the active or particle Lorentz symmetry breaking. You actually are saying that if your particle goes in that direction, it's different if it goes in that direction. Why it's different? Because there is a background vector there. So the definition for an elementary particle, the irreducible representation of the Lorentz group is intact.
Okay, so I hope that this answered your question, Albert. The other comment? So I'm just curious about if you have explored the impact of this Bumblebee and the benefit decays in the universe. If it has some impact on gravitational wave background, maybe the present of the longitudinal mode is present early universe, but then decays. But there is an explicit symmetry. So it is some risk just expect this process to have some impact background of gravitational.
Well, the audio is actually cutting, but I think you are asking if there is some how can you relate these results of the longitudinal modes decaying with time in the gravitational sector. Is that right?
Yes, correct.
Okay, so here we just consider the background there. We didn't consider the gravity dynamics itself. If you consider it, usually the models which we are in the literature just consider the vacuum corrections in the Einstein equations. So you consider, for example, usual Einstein-Hilbert term plus some corrections on the curvature coupling to this background vector. You can see this. It's a kind of non-minimal coupling between gravity and this background field, and that's all. Because I've never seen, maybe I'm wrong, but I've never seen just the term Einstein, Bumblebee, and a potential, and you solve these equations. So usually you have Einstein, non-minimal terms, the kinetic term for the Bumblebee, and that's all. Usually you don't consider the potential. So what I think we are working with Leandro, which is my PhD student, we are considering the modifications right now in the Einstein equations. When you consider Einstein, it's a kind of extension of Einstein-Maxwell system. It's an Einstein-Bumblebee kinetic term plus the potential, and we take only the linear terms of the Bumblebee and the Bumblebee potential. So I think what we're gonna see is that if you just take Einstein and Maxwell, for example, for a black hole, you have just the mass and the charge of the black holes as his unities. And if you consider Einstein, Bumblebee, kinetic terms, and the potential, I think you may find some kind of hair. And this hair might be related to this longitudinal mode. This longitudinal mode decays with time, and we have to see how it also spread all over the brain, all over, for example, spherical symmetric solution. Maybe this hair is unstable. So in the beginning of the formation of the black hole, maybe the longitudinal mode has some particular properties interesting for heavy compact objects. But then as the time goes on, I think these additional terms, it's suppressed in time. But it's just a guess. We are working on it.
Okay, thank you. Thank you for your...
Nice. Thank you, guys.
Thank you again. So our next speaker is Daniel Blixt. So let me see if I can make you send. Hi, Daniel. How is everything?
Hi. Good.
So, can you now share your screen? I think that your presenter, you should have 4 buttons at the bottom. One of them. Oh, okay, very good.
So it won't?
Yes, perfect. We can see it.
Okay. Yes.
So,
okay. So my talk. Oh yeah. Sorry.
No, I mean, you can start. We have 4 minutes, but you are full of energy. Okay, let's go with it. Please go ahead.
Okay, so my talk will also be a bit related. It will be a related breaking of Lorenz symmetry, but in kind of different way, and there is not really a need to suppress it in the same way. So basically, in principle, this metric teleparallel theories of gravity in couple stuff to the matter sector, and I think then you would get something similar to the previous talk. But these are this breaking of Lorenz symmetries basically exciting some extra fields. So yeah, basically we'll discuss the viability of metric teleparallel theories of gravity, and of course the motion is that if we consider some modified gravity, then important to understand if it's viable. And what is was at least to me quite astonishing is that general relativity has different formulations, and one of the formulation is the parallel formulation instead of a curvature formulation of Hilbert. So it's quite natural to ask if we can construct teleparallel theories of gravity. And another point is that, okay, so I have been exploring a lot the healthiness of theories, and recently, or yeah, quite some time, I have been investigating if it's possible to relate something called partially massless spin-2 field, which have not been successfully constructed before. And also I will discuss some other potentially healthy teleparallel theories. And if time allows, I will also talk a bit about developments of numerical teleparallel relativity, which you can look at the equivalent to relativity, and mathematically it will be the same, but perhaps there is some numerical advantages for it. So to understand these equivalent theories of gravity, we need to understand what is teleparallelism. And let us consider a general linear connection, gamma, which we do in the fine theories of gravity. And the simplest way to realize this equivalent is that we consider the Ritchie scalar of a general connection, and it can be decomposed into the Ritchie scalar of a Levi-Civita connection, which is used to formulate Einstein-Hilbert formulation, a torsion scalar field, something called non-metricity scalar, and then some mixed terms and a total derivative. And historically, teleparallel theories of gravity already assumed that non-metricity was zero, so this Q is zero. But in general, what the name suggests is that if you do a transport of a vector, then in contrast, when you have curvature, vectors will remain parallel. And for that, we demand that curvature is zero on the left-hand side. And because it was assumed that non-metricity is zero, but it doesn't affect how the vector rotates, it's better to call it metric teleparallelism when you assume that Q is zero. So this will be done in this talk. So Q is the left-hand side is zero. So it's quite easy to equate the scalar in terms of torsion. You can rewrite this Einstein-Hilbert action like this. So it's a torsion scalar, and then there's a boundary term. And normally we drop this boundary term and we call it teleparallel equivalent to relativity, which is class equivalent. It will give the same equations of motion. So that's the key point about the equivalence. Similarly, you can do this for non-metricity, and you get 3 corners, classically equivalent theories. Einstein-Hilbert formulation with curvature, Telepara or metric parallel equivalent to general relativity with torsion, and then symmetric Telepara equivalent with non-metricity. And it was asked what's like in thing which happened this year, and for me, I defended my PhD thesis, and what was in my thesis was that I derived for the first time the covariant Hamiltonian for f of t nu gr theory. So I will explain what this is. It's a very general teleparallel theory. And covariant formulation is some inclusions of a spin connection which have a global Lorenz symmetry. And it has been considered a lot in the literature. So basically we made a review, and in this review like some steps towards the Hamiltonian were made, and we did a big comparison among the literature of Hamiltonian analysis, and then in my thesis extended it to the full covariant Hamiltonian. So my point of view of teleparallel theories of gravity can be summarized by this map. So starting from the teleparallel equivalent to general relativity, as we do in f of r, we can consider f of t. However, f of r and f of t, they are bounded term in argument. So this gives linear non-trivial contributions when you take an arbitrary function of it. So it's not something that just vanishes. So physically we get 2 different theory, also classically, you consider f of t. Another construction is called new general relativity. This is where you consider a more general theory, which is at most second order in derivatives. And of course, you can also add some parity violating terms. You can even add just have Tager and parity violating terms. And what I studied was this f of t nu gr, and the motivation was to do it more general, and then I can just go to the limiting cases. And then there are some other ways to do modified gravity, and that is to exploit what we already know in modified gravity. So we already know some theories which are based on the Levi-Civita-Ricci scalar, and we can construct a teleparallel equivalent to this modified theory of gravity. And then we can play around with torsion, and we can create something new. And this basically summarizes the theories we know through the literature. And so I have been saying that my main result was related to the Hamiltonian analysis. And what it does is it gives you a count of a number of nonlinear degrees of freedom of a theory. And it's given, and it also gives some constraints. And they are classified in first class and second class constraints. And the total number of degrees of freedom is given by the total number of canonical fields, which are those which have time derivatives, minus the number of first class constraints, minus half of the second class constraints. So what is this good for? what are the applications? So if the degrees of freedom matches those found by perturbation theory, so if we calculate this number of degrees of freedom and then we do perturbation theory and count the number of modes there, if they match, we can trust the perturbation theory. However, if there's a discrepancy, if there's a jump in number of degrees of freedom, there's something called the strong coupling problem. And then it's very bad news for your theory, because then your perturbation theory cannot be trusted. And this happens in f of t gravity and parity violating terms. And there's also happening in new general relativity. So it seems that it happens a lot in teleparallel theories of gravity. So when we formulate our theory, we need to be very cautious that about the viability. And what does first-class constraints tell you about? They correspond to a symmetry of a theory. So it could, for example, be a Lorenz symmetry. So it's very clear from a Hamiltonian analysis, when you deviate from the equivalent to general relativity, you start to break some Lorenz symmetry. And another thing which you can find is that you need to demand that your constraints are conserved in time, and for that you get a matrix of Poisson brackets among constraints. And something that seems to happen when you have a strong coupling is also that these have some variable ranks. So depending on the field values, the number of degrees of freedom is it. So we suspect some bifurcations. So the number of degrees of freedom depends on your like base space where your theory lies, and it might be that you need to be restricted in some region for it to be viable. So because f of t nu gr and new general relativity, they have basically the same perturbations around Minkowski, and there are three pieces. So in teleparallel theories of gravity, in addition to the symmetric modes, you can also excite some antisymmetric modes. So we call the symmetric modes H, and so this H piece is related to the massless spin 2 field of which we have in general relativity. And you have some antisymmetric mode, and then you can also have some mixed mode. And this have also been done in 4 and some other places. And it appears through this master thesis that if you include all of these, so you demand that none of them is vanishing, then everything is first-class constraints, and you get 6 extra degrees of freedom. And then you don't have any strong coupling problem. And you violate completely this Lorenz symmetry, which you have a freedom to break. However, this last piece is a ghost field. So we want to keep the green piece because it's related to gravity. And the last piece we want to erase because it's a ghost, and we're left with this antisymmetric field, which turns out to be a Kalb-Ramond field. And in at lowest order, this is a massless pseudo-vector field. And then when you go to higher order, this is breaking. Like you excite more degrees of freedom. So perhaps this could be a massive Calibramon field. And this would be quite good news because through the Hamiltonian analysis of this theory, you have 5 degrees of freedom. So 2 for a massless spin 2 and plus 3 for a massive. So it might be just that you have to go to this higher order, which is 2 orders higher than written here, and your theory might be viable. But you should not trust the results of perturbations. Some result is saying that when you have only these two, you get the same like PPN parameters and solar system test as general relativity. This is not true because the field is strongly coupled. So in order to know what is actually happening, we need to go to a higher order, and then it might be safe. And for f of t gravity, so we assume these two are vanishing. We only get 2 propagating modes here, but the Hamiltonian analysis reveals that you have 5 degrees of freedom. So we have also a strongly coupled field in f of t gravity. And to illustrate the parameter space, we have this blue point is equivalent to general relativity. This red line is adding this Calibramon field, and the central point, the massless spin 2 field disappears, so this is only a Calibramon field. The white region is the most generic one, which has a ghost, and for the other places, you will remove modes from your gravitational spin 2 fields. So basically, there's only a question mark if this red line is viable, but the other regions can already be excluded. And also non-linear extensions like f of t. So an idea about partially masslessness, which I have, is that it has been considered already in bimetric gravity. And what partially masslessness means is that you think that you about a massive spin 2 field, and this will have 5 degrees of freedom. But then you have an additional conformal symmetry, which removes the scalar helicity mode from the massive spin 2 field. Then you're left with only 4 degrees of freedom. And this is called partially masslessness because it has been found that in around some backgrounds it will become massless, but around other backgrounds it's expected to be massive. And so it has 4 degrees of freedom instead of 5, as I said. And it appears through this special interaction in the traditional Hassan-Rosen bimetric gravity theory. And this removes two interaction potential have been dropped out, which are like break some symmetry of 2 tetrads, and you get an enhanced symmetry and remove 1 degrees of freedom. However, when people have looked into such theories, you also have a strong coupling problem. And another point is that there's generically in bimetric gravity so-called a Higuchi Ghost, and that requires that this theory has to be in a de Sitter background to avoid this ghost. So a previous attempt to do this in an alternative way to the Hassan-Rosen theory is to introduce this psi, which are complex tetrad fields, and then you construct your Riemann curvature tensor and Ricci tensor in terms of these complex tetrad fields. And since it's very hard to make the Ricci tensor cancel like real, if you make it depend on complex tetrads, you have to take the real part here. And then there is some vector field also introduced. And so this looks a bit ugly, and it turns out that also this gives the strong coupling problem. So my idea is that what if we complexify Telepara equivalent to general relativity? So in my notation, I use this Danish A for the complex tetrad field. So so when you complexify, it's like having two tetrads, one purely imaginary and one purely real. And let's consider a formulation of equivalence to general relativity, which looks like this. And here we just take this tetrad E and complexify it. So also this contortion, it depends on torsion, which depends on E, the tetrad. So we just promote this E's to be A, and each second, if we put the complex conjugate, the whole action will be real. And you also get this interaction potential. And to me, this looks much nicer. I mean, and much more straightforward to think of. So the idea is to explore this. And what the content is an easy recipe to remember. There's a spin connection, the covariance of a theory, two tetrads, three interaction terms. I mean, this is written in a compact form. If you expand it into the real part, you will see that there are three interaction terms and 4 new degrees of freedom, which are the partially massless fields. Yet we have to do perturbation theory around the Sitter backgrounds to see if it's really healthy. And what are the pros and cons? The cons is that this is a Telepara theory, and normally they have a strong coupling problem. But now we have used the Telepara equivalent to general relativity, which is a special case, which avoids the strong coupling problem. So maybe that's one part, which is a promising thing. And it looks beautiful, but I use this differential forms and contortion, and it's hiding a lot of stuff. So it's actually more complicated than it looks. And also, I don't know, I'm not aware of any evidence for partially masslessness. But it would be nice to predict and constrain by observation. And it's also out of curiosity, can we create a viable theory of partially massless fields? And pros is that it definitely looks more natural, not as ad hoc as the last one, at least to my taste. And complex fields are important in quantum field theory and quantum mechanics. So maybe we should try to do something similar for gravity. And the Sitter backgrounds, they make most sense to investigate both in bimetric gravity and in teleparal gravity. So in bimetric gravity to avoid the Higuchi Ghost, and in teleparal gravity because you can expect that if you have a less trivial background, you might excite more degrees of freedom of your perturbation theory, and in that way you might avoid the strong coupling problem. Sorry. Let's see how much time. Okay, maybe I can quickly talk about numerical telepal relativity. So basically we need to do a 3+1 split in order to do time steps of numerical simulation. And it's important, of course, also that this formulation is unique and that these two don't overlap with each other, because we will lose predictability. And there have been a recent article about numerical relativity for the trinity of gravity, and there they derive evolution equations, and those are always formulated in a theory independent way. So you evolve the fundamental fields, and then you add the equations of motion afterwards for your theory. And after you do that in GR, those turns to linear differential equations, and then they can be solved on a computer. What is curious about this article is that it was okay for the symmetric Telepara equivalence to general relativity, but not for Tegger. And so basically when they applied the equations of motion of Tegger to the evolution equations, they didn't become linear differential equations. So I got a bit curious, why is that? How can we improve? So me and some people in Tartu, we have some guesses. So in this article, they formulate everything, including the geometry, like the hypersurface geometry, like extrinsic curvature and so on, by a generalized connection. And perhaps this is not the right thing to do, because you have an equivalent theory, like your geometry, background geometry, like your physical geometry should be the same, even though the mathematics are different. So we have to look deeper into these foundations of a formulation. And because of this, maybe this integrability condition might be broken. So basically, that these hypersurfaces would cross each other. So we also plan to check the integrability condition so that the formulation is fine. And the third thing is that fundamental fields are tetrads. They have 6 more degrees of freedom. They are also like the 6 extra degrees of freedom are related to breaking of Lorenz symmetry. So because this theory, like general relativity, it has no breaking of Lorenz symmetry. So it means that there are 6 supplementary constraints of this theory. And maybe these ones were missed out. And if we formulate them, we might be able to like solve nonlinearity. So what do I see for the future? Yeah, one project is to derive Hamilton's equations in Telepara theories of gravity, because this has not been derived, and it's also related to numerical relativity. Then also to develop numerical Telepara relativity, and to understand the classification of constraints into first and second class better. I was mentioning that we had these weird bifurcations and stuff, so I would like to investigate this more. And of course also to do these perturbations in this partially massless theory. And a promising direction for numerical relativity is to check integrability conditions, which I was mentioning, and also that we should develop a Telepara BSSN formalism, because BSSN has the numerical stabilities. So that's some future projects I would like to investigate. And I have a final sentence, and that is that according to my experience, it's very difficult to find healthy teleparal theories of gravity. So thank you.
Okay, so thank you, Daniel, for this nice presentation. I think that Albert has some questions. I don't know if anybody else wants to ask anything, but I will start with Albert's questions.
Yeah.
He's asking Sorry?
Well, thank you for the possibility to ask a question.
Okay.
My question will be the following. Did anybody try to calculate loop corrections in teleparallel gravity? Because as I know, there are a lot of calculations in metric gravity of loop corrections.
Yes, that's a good question. And as I am aware, there is nothing. There is some echo, I don't know why.
Nice.
So as I am aware, there is nothing like that done. Not so much have been done in the quantum gravity direction, I think. And it's very interesting because this differs by boundary term. So we expect some differences.
Thank you.
Maybe now I think Euclides want to ask something as well.
Okay.
Euclides, can you speak, or maybe you can write it and I can formulate it for you?
So in Hassan-Rosen potential, normally it's written in terms of two metrics and elementary polynomials of like the square root of a combination of them. So this can also be expressed in tetrad formulation. And yeah, basically what I did was that I complexified Tegger and added this potential. And I mean, you can add 2 copies of Tegger and plus this potential, and you have equivalent to Hassan-Rosen bimetric gravity. So this is like this part. And what I did was that I played around a bit and went to this part. And this construction is like very similar to what was previously done. Actually, Fawad Hassan was one of the authors here. So it's like an alternative way to formulate some kinetic term, but then you need to use complex fields.
So if there are no more questions, I would like to ask, do you know, like, as far as I know, but I am not an expert on this, bimetric theories generally have some problems associated, like generally they have like pathological couplings between the two metrics and things like that. Do you know if that will happen in this complexified version of Tegger?
So bimetric gravity, you should only couple like one metric to matter to avoid such problems. I think that is the problem you were referring to. And I think something similar will happen if you would couple both to matter. So
okay.
Normally, yeah.
So I would also expect, I don't know, but I would also expect that if you couple the two metrics between them, maybe there is some like special kind of coupling which avoids instabilities, but in general, it will not happen. Like you might need a specific fine tuning for coupling the two metrics.
You mean this Bowler Desert stuff?
For instance.
Yeah. So basically this potential is constructed so that it avoids this problem. So this is done for Hassan and Rosen, and now I just consider a subcase of this with an enhanced symmetry to try to explain partially masslessness.
And do you know if the way they build this potential, like, is there any kind of symmetry protecting these couplings or things like that? Or they just like find it and that's all?
Yeah, I'm not aware about the details of the derivation, but basically what happened, the basic idea is that when you introduce the second tetrad, you still have only one global diffeomorphism invariance, and so the second tetrad has like 4 more excited degrees of freedom. But this potential is constructed so that when you do the Hamiltonian analysis, it generates secondary constraints, which removes this pathological like sixth one, because you only want 5 more. So that's the basic idea.
Okay, thanks. If nobody wants to ask another question, which I think anybody wants, maybe it's time to introduce the next speaker, which is Ana Alonso from I think the Albert Einstein Institute at Potsdam. Maybe correct me if I am wrong. And she's going to talk about time machines in quantum field theory, basically 1+1 model. Like the time traveler's guide to quantum field theory is the title of her talk. So Anna, can you share your screen?
Hi, nice. Thanks for the invitation and for the opportunity to present. And no, I think I cannot share the screen. It should be in the lower part of the.
Okay.
In the bottom, isn't it? Oh, now I can.
So I think we are.
Yeah.
Okay. Yeah.
You can see it?
Yeah.
Okay. So what I'm going to present here is a paper that we have published very recently. That the title is very similar to the one that I set for this talk, but there is a subtle difference that in the paper we say that is the guide to quantization of zero modes, because it's the specific part that we have done in this paper. And I said to quantum field theory in order to present the possibilities that it's opening this project. So this is a paper I made in collaboration with Erickson Choya, Luis Garay, and Eduardo Martín Martínez. And the main idea when we started thinking about this was trying to deal with time machines and the problems that are associated to them. I don't know if you listen to me good, or I should modify the microphone. It's okay?
For me, it's okay, at least.
Okay. Okay, because usually I have problems with the microphone in this computer. So, okay. So then we started thinking about these time machines and how to construct it, and we end in going to the idea of making the time machine be a traversable workhorse, because it's something we.
Excuse me. Actually, it was better the audio before you did something. I don't know.
Sorry?
Okay. It was okay before, and now it's we listen to you a little bit.
Okay, now it's better?
Now better, yeah.
Perfect. Okay. Okay, so then the idea is to use traversable wormholes in order to create time machines and deal with them. And as you see here, that I put in I have high marked the paper. So there are, if we consider the existence of traversable wormholes, there are several ways that we can transform it into time machines, something that has been deeply studied in the past by Thorne, Morris, Friedman, etc. Like you can either identify directly the modes or moving the different modes at high speeds, or I don't know, different methods. And in fact, there are some results that we mentioned here that I think, if I remember, this reference 9 is from Frolov and Novikov, saying that a wormhole that is surrounded by matter, it will be transformed into a time machine. So that was the reason we use them. And I will mention explicitly later how we construct it. So then these traversable wormholes are transformed into time machine, and then this implies that they contain closed timeline curves. And in this transformation, there is something associated, that is that they will have Cauchy horizons. And this has been studied in the literature if these time machines are stable, relating it with the stability of this Cauchy horizon, and it's something that it can be also done in our framework. So in our framework, what we are trying to do is to develop a standard quantum field theory in these spacetimes. What is the complication of this? The complication is that in the moment that you have these CTCs, you have a spacetime that is multiply connected, and in these spacetimes that are multiply connected, we don't know how to do a standard quantum field theory. So one of the possible solutions to deal with that is to work in a corresponding universal covariant space to this multiply connected spacetime, and find a way of doing the quantum field theory, developing the quantum field theory in the covariant space, and then go transform it to the original time machine spacetime. So this is more or less what we are going to develop, what we have developed here. And let me first explain you, that is mainly what I'm going to spend most of the time, is to explain the geometry that we are using and how we consider these spacetimes. So by the sake of simplicity, we have considered only 1+1 wormholes. Also because these two-dimensional systems give us very powerful tools to work with. But the system could be generalized to higher dimensions with complication of the computation, of course, but not conceptually. So then the idea is that we have we construct a 1+1 wormhole just by doing a topological identification of the opposite ends of a strip. That's the easiest way to create this wormhole. And that space-time is completely equivalent, is the same that the Einstein cylinder that is created from the Minkowski space-time. So this is just the wormhole space-time without any time machine. And the easiest way to create a time machine there is developing that identification at different times. And with that, we create our time machine space-time. Okay, so with that, as I said here, we explain a little bit how this can be generalized to higher dimensions, like having two word lines and then cutting two balls where the mouths are and identify them. And it's working exactly in the same way that in this simple case of the 1+1. So then let me explain you a little bit the metric and the, in general the space-time. And please, if something is not clear, interrupt me. So then the first thing that we do is to consider a global static simply connected metric, and it's what we will call an auxiliary space-time M that will have this form that is here in expression 1. where this alpha is a positive function that is non-vanishing, so we will write it in this convenient form of the exponential of the integral of a parameter a. But this is not relevant now. I mark it here only because I will give a special example when we consider a particularly simple function a. So in this metric that is globally static, we have a unique Killing vector field that allow us to define our theory. Okay, so this is the auxiliary spacetime for math here. And then in order to construct our time machine, that is what we call the spacetime M bar, what we do is identifying the points in the previous spacetime, and as I said before, like the opposite ends. To do that, we use two constants. One is constant Q. I don't know if you can see my mouse. Yes, it's okay. The positive constant Q that gives us the length of the strip. So it's like the separation of the two mouths of the wormhole. And the other constant that we consider, that we will consider positive, is A. A is greater or equal than 1. And this A is what we call the work parameter, and what represents is the strength of the time machine. What it means is like when A is equal 1, there is no time machine. It's identified at equal times. And when A is greater than 1, it means that we are identifying at greater times. So it's giving to the strength of the time machine. So this is the way we establish this equivalence relation. And then the characterization of the system is very simple. In the case that we have A greater than 1, we have time machine, we have CTCs, and then we have future and past Cauchy horizon. When A tends to 1, we have a simple wormhole model. We recover the standard quantum field theory when I explain it in the quantum field theory in the Einstein cylinder. Okay, so another thing is like then this space-time with the time machine, as I mentioned before, is not longer simply connected, it's multiply connected. What we have is a system that is locally static. So it means that it has some regions that are static and they have a Killing vector, but globally it has not a Killing vector field. So what we have to do is to go to the covering space, and this covering space is not marked here when I put it in the paper. This covering space will be exactly this space-time M. So just as a summary, we will have this. I think I have it written here, the metric explicitly. Oh no, I have only a particular case later. Okay, so the idea is we have this identification that gives us a space-time M bar, that is the time machine. And the covering space of it is this simple connected metric M. So, and I said that I have not written the metric because in order to make things easier, we go to a particular example. And it's what I said before of particularizing this function A here to give a particular parameter alpha. And we give a simple value that is called W, that is the logarithm of the strength of the time machine, the work parameter, divided by the L, that is the distance between the two mouths of the wormhole, what I called before Q in the other metric. And this is what is the canonical time machine. And we can do this without any loss of generality because we are in 1+1 dimensions. So any metric is going to be conformal to this. So there is no any loss of generality. And then what we obtain, the metric we are going to work with is this simple metric. So what I wanted to arrive in the end is to say that this metric is going to be our time machine in 1+1 dimensions with the both streams identified. Okay, so once we have this space-time, also we have identified the CTCs and everything, we can go to construct the quantum field theory. Here I have written, but I'm not going to enter this talk in detail unless you are interested later. We are doing everything compared to the Einstein cylinder, to the wormhole space-time, in order to recover the result and to fix the zero mode, as I will explain. Because as you may know, in the case of the Einstein cylinder, you develop the quantum field theory and you have a contribution of the oscillator modes and a contribution of the zero mode that gives you an arbitrary contribution there. So then what we develop is the quantum field theory in our time machine model using the metric that I mentioned before. And the first particularity of that space-time that I wanted to mention is that the universal covering of that metric is the Poincare patch of ADS2. And this is clearly seen when you develop a change of coordinate to the standard Poincare patch coordinates given this metric. That is ADS2, 1. And of course, having this, you can go to the null coordinates, and this allows us to paint the Penrose diagrams that I wanted to show you to try to make clearer the space we are working with. So this is the Penrose diagram of our space-time. So the region that we are working with is this triangle here, and these H plus and H minus are the Cauchy horizons. So in this space-time, before the identification, there are no CTCs in this region, but there are CTCs beyond these two horizons. And this is the this triangle gives you the covering space. That is also the space-time before the identification, as I mentioned. Then when we develop the identification, that means when we create the time machine, we get a space-time that develops two new Cauchy horizons here, this prima H plus and H minus. And that means that in these two disconnected regions, now we will have CTCs. So the only region that will have not CTCs is this diamond here that is represented by positive null coordinates. And I wanted to be very explicit on this because in this paper what we have done is that we have quantized the field in all these paths because we have worked in the covering space. With that we have come back to the multiply connected space-time, but all the calculations we have restricted to this diamond by the sake of simplicity and to make connection with the Einstein cylinder. So then what we do here is the standard quantum field theory. We have our Klein-Gordon equation in the covering space, and we can find that any solution is right in this general mode, giving an expression 30. And this gives us the expression of the quantum field theory in the covering space. Now, how we can take the fields in the covering space and transform it to the ones in our time machine space-time? So for that, we use that the topological identification that we have done with the ends of the strips give us a connection, an identification in the null coordinates in this way. And this identification allows us to identify also the fields in the stream points. And this is what is called, I'm not going to enter here, as automorphic fields, and allow us to make the transformation. In this case, it's very simple because it's particularly given by this expression. In this will be much more complicated if we go to more general cases. So that was also one of the reasons to restrict to this simple case. So then with this trick, we can go directly to define all the annihilation variables and the modes in the time machine space-time. That will be, of course, then given in terms of this A. And this gives us to the final modes that are represented with a bar, because the space-time is the M bar, as I mentioned, and they are given by these two expressions in terms of the null coordinates. And in these expressions, I've marked this S plus and S minus, that is giving the sign of the coordinates. And this W here, that if you remember is what defines our metric. Let me be back to it here, as the logarithm of A divided to L. So W is what encodes the strength of the time machine and the separation of the modes. So everything of that is encoded in this parameter W. And then is what I said, all the calculations that we have developed from now on are only in the positive diamond, in the positive section of the spacetime, where we have no CTC. So everything we have done here is, to say in some way, outside the time machine. That is okay. So having the modes, we have all the tools to calculate the vacuum correlators, like we have working with the Weidmann function and with the Hadamard, that is the anti-commutator, and the Pauli-Jordan discommutator. So this is what I said, that what we have explicitly done here is to calculate this function in this diamond where we have no CTCs, and we have calculated the limit where A tends to 1. That is where we have no time machine and we recover the wormhole. And what we have found with that is that the fact of having the time machine gives fix the zero mode. So the zero mode that was arbitrary without the time machine, in the case that we have it and then we use it as a limit to recover the wormhole, we have fixed it. And so this is the main result we are discussing in this paper. Is everything. That's the reason of the title of the zero mode that I mentioned. But the point is that after having all of this, we think that this technique can provide more results. For example, having something that we have only mentioned here is that we can calculate the randomized stress energy tensor. In this case, we have done it also in the diamond, and we have seen how to apply to the Cauchy horizon, and then how we can argue for possible instabilities to enter into the time machine or not. And the other ideas from now on is like, okay, now that we have all this theory, what we can do here. So one of the ideas that we are developing right now is like introducing some detectors and see how the detectors communicate between themselves and which results you can extract from there. But there is like open possibilities for this. So yeah, I think that this is more or less the framework I wanted to present, mostly focus on which possibilities we could have for doing new things here. So thank you very much.
Okay, thank you, Ana, for this nice talk. I see that Ivan Agulló wants to ask some question. So Ivan, go ahead.
Yes, can you hear me?
Yep.
Yes. Hi, Ana. Hi,
Hi.
Adrian. Thank you for the talk. Could you explain with a bit more of detail what you mean by that the zero mode was arbitrary before? So what that means, and what you mean by it has been fixed? I couldn't fully understand what you had in mind.
Yeah, I mean, let me try to show you here. So find it. Okay, so here this is we have this expression for the zero mode, so we will have it as a function of this position and momentum operators here, but we have not a prescription to fully specify it, and I'm not sure if we have it where I have it written. One moment. But then when we have done our prescription here, okay, you see that when we do the quantum field theory, we see that it is expressed this momentum in terms of a parameter, a dimensionless frequency parameter here. And what we have found, as you see, this is the expression of the correlators in terms of this gamma in the case of these correlators of the zero mode contribution to the correlators in terms of gamma. So then when we have done this development, we have found an explicit contribution for that limit that should be written here in these expressions. Yeah. If I manage to find it.
Okay, so
Yeah, I don't know if it was clear to you or I was.
It was a bit fast because you were moving up and down. I couldn't see the expression.
Sorry. Yeah, sorry. Also, it's the first time that I give a talk with a paper. I'm sorry if I was very messed because it's more difficult than I expected.
Right, but I think I got the idea. I will take a look to the paper.
Thanks.
okay, so any other questions in the audience? Okay, if not, I wanted to ask you one, because at some point you said that the space after topological identification looks like a cylinder.
Mm-hmm.
Okay, so okay, I will try to think about, because it somehow, like, the fact that you want to identify both, like, so are you identifying points that satisfy both conditions, t prime over t equals a and x minus x prime equals q, or points which satisfy any of those conditions?
No, it's an equivalence relation on the two of them.
Okay.
And the cylinder is when A is equal 1.
Okay.
It's when you recover the cylinder. That is the wormhole case.
If A is different from 1, maybe bigger, do you know what kind of topology do you find?
Yes, it's kind of a cylinder, but it's a little bit complicated because you cannot divide it you cannot split it into Cauchy surfaces. You have some other topology that was nicely explained by Gerog. So it's kind of like, I don't know how to visualize it, like a cylinder, but like a spiral, because it's identified like a spiral like this.
Okay, thank you.
It has a kind of complex topology, but in the case of 1+1, it's pretty simple to work with.
Mm. Okay. So, any other questions in the audience? If not, let's thank Anna again for the nice talk, and let me introduce the next speaker, which will be João Paulo Beza Brito from University of Federal University of Pará. He's going to give a talk about radiation emitted by a source orbiting Schwarzschild's ADS black hole. So, João Paulo, are you there? Mm. Can you hear us?
I was just muted, but I already find it how to
Okay.
share my screen. Thank you.
Okay. Okay, so go ahead whenever you want.
Initiate my cam. I'm sorry for the delay.
No, it's okay.
So, hello everyone. I am João Paulo Brito, a PhD student of the graduate program in physics at the Federal University of Pará. And today I'm going to talk about radiation emitted by a source orbiting a Schwarzschild anti-de Sitter black hole. This presentation is based on a work accepted for publication in PRD and made in collaboration with Rafael Pinto Bernay and Professor Luis Crispino. Well, this is the outline of the presentation. We begin with a short introduction where we give motivation and references. In sequence, we revisit some features of the Kotler space-time that will be our background. And we quantize the scalar field in this background using the canonical quantization prescription, such that using quantum field theory in curved space-times at tree level, we compute the emitted power by the source orbiting the central black hole along circular geodesics. And in the end, we give some final remarks. Well, in the second mid of the 60s, Leonard Parker established the quantum field theory in curved spacetimes by investigating the particle creation in expanding universes. He basically used the Bogoliubov transformation techniques to show that a changing gravitational field would produce particles. This is a mechanism that was suggested to be responsible for the climp of matter in galaxies at the early universe, for example. This new theory has reached in very remarkable results, such as the particle creation by black holes, reported by Stephen Hawking in 1975. And another example is the Unruh effect that states that the particle content of the theory is observer dependent. In fact, the Unruh effect was reported in 1975 during the first Massel-Grossman meeting, but the proceedings of the meetings was published only 1 year after his paper of 76, in this case in 1977. Well, at the same year of Parker's paper, Joseph Weber reported that he had evidence for discovery of gravitational radiation. This was a goal believed to be impossible at that time, and soon he became a very famous person, but in fact, he did not observe gravitational radiation. But it turned out to be interesting because many people tried to interpret his observations, such as in this paper by Misne of 1972, in which he suggested that if the source of the radiation observed by Weber was in the galactic center, it could be a reasonable explanation if the source was emitting synchrotron gravitational modes. This kind of radiation consists of a beam, a flux beamed at the plane of the orbit. In this case, in the equatorial plane of a black hole, if the source is considered orbiting the black hole along circular geodesics at this plane. So this idea was further developed in this other paper where they give the tailored analysis in the scalar case, and from this they inferred that synchrotron gravitational radiations should exist in this simple scenario where the source orbiting the black hole along circular geodesics. But it was soon realized in this other paper that the spectra of the three types of radiation, scalar, electromagnetic, and gravitational, are in fact drastically different, such as that in the gravitational case, the lower multipolar modes have a significant contributions. So, but in spite of that, these investigations have its own importance because in the context of high energy astrophysics, the phenomena of spiraling matter around black hole have great importance. So this simple phenomena can be analyzed through a semi-classical approach with quantum field theory in curved spacetimes. And this was first done by Crispino, Higuchi, and Masslessness in 2000s, where they calculated the emitted power by the source orbiting a Schwarzschild black hole along circular geodesics. In fact, their formalism can be readily adapted to investigate other interesting phenomena such as the Hawking radiation interacting with the sources outside the black hole and so on. Well, since then, other interesting investigations have been published so far, analyzing the geodesic synchrotron radiation, especially in asymptotically flat spacetimes. But it could be interesting too to analyze these phenomena in spacetimes that are not asymptotically flat, such as the spacetimes asymptotically de Sitter or anti-de Sitter. In the context of anti-de Sitter, there is an investigation in the Schwarzschild anti-de Sitter geometry performed by Cardoso and Lemos, in which they calculate the power spectrum by a scalar charge moving around the Schwarzschild anti-de Sitter black hole, and this was done using the classical approach of the Green's function. In the context of Schwarzschild de Sitter black holes, we already have performed an investigation calculating the emitted power by the source of the Schwarzschild de Sitter black hole. So we can use these results to compare with the present results, in which we use a quantum field theory in curved spacetimes to calculate the emitted power by a source orbiting Schwarzschild anti-de Sitter black hole. In this case, these spacetimes mentioned was obtained by Kotler in 1918 and are in fact a solution of Einstein field equations with cosmological constant, such as the Kotler solution is given by this line element here, where the radial function is defined in this way, such that for lambda 0 we have the Schwarzschild spacetime, and positive lambda we have the Schwarzschild de Sitter spacetime, and negative lambda we have Schwarzschild anti-de Sitter spacetime. So basically, the spacetime consists of a Schwarzschild black hole in a spacetimes that are asymptotically flat, de Sitter or anti-de Sitter. So what we do in this work is quantize the scalar field in the Schwarzschild anti-de Sitter, SADS for brevity, and calculate the emitted power by the source orbiting the black hole as represented in this picture here. And to to do that, we have to obtain the one particle emission amplitude that in perturbation theory at first order is given by this expression here, in which S hat is the interaction action that represents the interaction between this classical source with the quantum field. Well, in order to account for the motion of the source, we have to study the geodesics of the Kotler spacetime that can be derived from this Lagrange as in the usual way. And using all Lagrange equations, we obtain these ordinary differential equations where the capital E and capital L are conservative quantities related to the symmetries of the spacetimes. In this case, the time-like and axial Killing vectors. Here, epsilon is a constant that is -1 for time-like orbits and 0 for null orbits. Regarding circular orbits, circular geodesics, we have a light ring given by R0 equals 3m that is independent of lambda, and the angular velocity of time-like circular orbits given by this capital omega. In the case of Schwarzschild-Sitte, lambda lies between 0 and 1/9 in order to maintain the black hole structure of the spacetime. In this case, we have a inner event horizon and a cosmological horizon. And circular orbits occurs only in a narrow region delimited by the photosphere of the black hole and this position Rmax that marks the position of the maximum of the radial function. So in Schwarzschild-Sitte, we have this static region between the two horizons, such that we can quantize the scalar field as outside the Schwarzschild black hole. Well, in the context of SADS spacetimes, lambda lies between -infinity and 0. In this case, we have an event horizon, RE, and a natural length that is given by the Untitled Chapter radius, defined in this expression, and the observer radial position given by this expression. In this case, circular orbits exist outside the photosphere of the black hole, in which the angular velocity of time-like circular orbits have a minimum value as R tends to infinity and a maximum value at R0. Well, the scalar field in Kotler spacetime can be derived from this Lagrangian. Where in this Lagrange, we obtain the Klein-Gord equation, where G is the determinant of the metric and G mu nu are the contravariant components of the metric, such that the positive frequency solution to this equation is obtained in this way using the symmetries of the spacetime, in which capital Y are the scalar spherical harmonics, and the psi function obeys this differential equation that can be put in a Schrödinger-like form if you use the tortoise coordinate of the spacetime. Well, the effective potential defined in this expression in the Schwarzschild-Sitte, or SADS for brevity, the potential barrier decreases as you increase lambda, and in the Untitled Chapter, SADS, the potential barrier increases as you decrease lambda. In SADS spacetimes, we have points of maximum and minimum of this potential, and that gives rise to long-lived modes, for example. So we can use the inner product to normalize the modes in which the capital sigma is a T constant hypersurface. This hypersurface is a Cauchy hypersurface in asymptotically flat spacetimes, such as the Kerr-Neumann family, and as well as in Schwarzschild-Sitte. Well, regarding the boundary conditions, in SDS spacetime, we can use reflective boundary conditions that is given by are given by the so-called in and up modes, where the in modes are the modes purely coming from the past cosmological horizon, with partly transmitted to the future event horizon and partly reflected back to future cosmological horizon. While the up modes are the modes related to the modes purely incoming from the past event horizon, with partly transmitted to future cosmological horizon, and partly reflected back to the future event horizon. In this case, capital A are overall normalization constants that we will obtain later, and T and R are related to transmission reflection coefficients that obeys this conservation equation, and here R star is the tortoise coordinate. So in the case of Schwarzschild anti-density, we have to choose suitable boundary conditions at infinity to obtain a well-defined field theory. In this case, we choose reflective boundary conditions such that we end up with these two independent modes that we call psi1 and psi2. Here again, capital A are overall normalization constants, and by considering the Wronskian of these two solutions, we obtain this condition for the coefficient B. That is a conservation equation. In this case, ρ is related to R by this definition, psi with small psi with this transformation. Now, the scalar field quantization can be performed in the usual way in a static space-time, that is expanding the field operator into negative and positive frequencies, in which the creation annihilation operators satisfy this set of commutation relations. In the vacuum state is defined as the state destroyed by the application of all annihilation operators, and the one particle state is constructed by applying the creation operator into the vacuum. In SADS case, the modes, the positive frequency modes is given by this expression that obeys these orthogonality conditions, and using the inner product and this form for these modes for the psi function, we can obtain the overall normalization constants given by this up to a phase for k range representing the modes 1 and 2, and omega bar is defined as this expression. Okay, so the scalar radiation and emitted power can be obtained by considering an interaction term by adding an interaction term to the action. This interaction term represents the coupling between the classical source represented by this current and the quantum field. In this case, the scalar source is considered orbiting the black hole along circular geodesics with a full velocity given by this expression, where U0 that appears here is the time component of the full velocity. So here, alpha can be regarded as a coupling constant that determines the magnitude of the interaction between J and phi, such that we can obtain the one particle emission amplitude using this expression. Expanding this expression, we obtain that the amplitude is proportional to this delta. That means that the frequency of the frequency of the quantum will be proportional to the angular velocity of the source, in a way that the proportionality constant is the azimuthal number. So the partial emitted power for fixed values of L and M can be obtained using the early result for A, given by this expression, where capital T is considered as the whole time coordinate that can be written in this form, such that when we expand this equation here, we obtain explicitly for the partial emitted power as this. In this case, the power will vanish if the if the radial position of the orbit tends to the photosphere of the black hole, if L plus M is an odd number, because this term here that vanishes, and if R goes to infinity, because this term here vanishes. Furthermore, for even values of L plus M, this term can be written in this form. So with this, we can obtain the total emitted power by summing all contributions of the multipolars, in this case, for the contributions of M and L. But also we use numerical computations to obtain the psi functions here. We have to truncate the sum in a maximum value of L. So in this case, our numerical computations is given by the following. Once the physical horizon and infinity are not reachable by numerical computations, we have to define a numerical event horizon that is slightly bigger than the event horizon, and the increment is given by this delta, in which can be defined of the order of 10 to minus 5, for example, and the infinity is a big number, although finite is a big number only. That can be defined in this way. So with this, we integrate the differential equation, obtain the psi function in this region between the numerical horizon and the numerical infinity. Well, now we show the results for the emitted power. First of all, I would like to mention that more than 98% of the emitted power comes from the modes with L equal M, such that in the following we show only these modes. Here in this figure, we plot the partial emitted power for lambda equals minus half as a function of capital omega, the angular velocity of the source. Omega ranges from omega minimum when the orbital position is at infinity, and omega max when the orbital position is at the photosphere of the black hole. In this case, we choose the first 20 values of the index L, and that is our multipolar number. We see that the emitted power starts from 0 at infinity, reaches a maximum near the photosphere, and decreases to 0 again at the photosphere of the black hole. Furthermore, the peak of the partial power approaches the photosphere as you increase the multipolar number. We can plot this for smaller values of the cosmological constant, for example, lambda equals minus half here. And we see that there is a little enhancement in the higher multipolar sector, as can be seen by comparing these two figures. For smaller values of the cosmological constant, this effect becomes more evident. For lambda equals minus 3, that corresponds to a black hole of the size of the anti-density radius in this case, and we observe this effect. And for lambda smaller, even smaller, we see that for minus 5, for example, the L equal 20 have the predominant contribution in the emitted power. But I have to mention that in spite of this enhancement of the higher multipolar modes, the power is dominated by finite multipolar modes, such that this can be better seen in this figure, that where we can plot the emitted power for some values of multipolars only for stable orbits. We see that the contribution to the emitted power increases as you increase L, but after a maximum value of L, in this case L equal 5, the contribution starts to decrease again, such that the L equal 20 have a small contribution. Well, we can show too for the total emitted power the total emitted power as a function of the angular velocity. In this case, for lambda equals minus half. For some values of L max, the maximum value in this sum. And we see that close to the black hole, higher multipolars have the predominant contributions, the predominant contribution, because in this case, the source are emitting synchrotron radiation, but far away from the black hole, the higher multipolar modes have a negligible contribution. So here are final remarks. We numerically calculated the partial and total emitted power using quantum field theory at 3 level in the Schwarzschild anti-de Sitter spacetime. And we shown that the emitted power strongly depends on the value of the cosmological constant. And our results is in good agreement with the classical results obtained by Cardoso and Lemos in 2002 using the Green's function technique. And in particular, this behavior is in some sense the opposite of the one that occurs in Schwarzschild de Sitter black holes, where we see a enhancement of the lower multipolar sector. Now we can use the present formalism to analyze other interesting phenomena related to other more realistic fields, such as the electromagnetic or the gravitational field. So this is that I have to say for now. Thank you for your attention.
Okay, thank you very much, João, for the nice presentation. I see people clapping in the main room. So, is there any question in the audience? So, Ivan, go ahead.
Hi. I have two questions. Let me ask one, and then if nobody has questions, I will ask the second one. The first one is the following. You started your talk, reminding us about the results of Parker, Hawking, Unruh, of spontaneous particle creation from the vacuum in a time-dependent space-time. And I was expecting that physics to appear later on, but rather what you explain is how a source around a black hole can emit radiation. Is there any relation between the two phenomena?
In principle, no, but the formalism used can be the formalism used here can be used to analyze other phenomena related to the Hawking radiation, for example. That is the interaction of the Hawking radiation with sources outside black holes. There is already some investigations in the literature about this using the formalism presented here of the quantum field theory.
But your talk didn't contain that part, right?
No. In this case, we consider only the source orbiting the black hole and emitting radiation.
I see. So nothing like particle creation a la Hawking or a la Parker has appeared in your calculations yet.
No.
And the second question is I have difficulty in intuitively understanding why the cosmological constant plays such an important role, right? So you have something around the black hole which is emitting radiation, a source, and why something related with the cosmological constant, right, which has to do with asymptotic properties of the space-time is so relevant. Can you help me to understand intuitively?
The motivation to study asymptotically the Sitter, for example, is due to the fact that there is experimental evidence of that our cosmological neighborhood is undergoing accelerated expansion. I don't know if is that you are asking?
No, I understand the motivation, of course, because we live in the Sitter probably. But I would expect that if I go close to a black hole and I see the radiation emitted by a source, I would not if I am in the Sitter, anti-de Sitter, or Minkowski. But you told me told us that the power emitted depends highly on lambda, and I was kind of surprised. Is there an intuitive way to?
In fact, the results that depends strongly of the cosmological constant, but we know that the value of the cosmological constant is very small So we shouldn't be able to observe this difference in our observations, for example, because the cosmological constant is the order of the 10 to minus 52, I think.
So if you put the real value, these effects are completely negligible, right?
Yeah. Yes.
Okay. Thank you.
So I think that Luis wanted to add something maybe or ask another question.
Yeah, it's just that, well, thank you, João, for your presentation. Thank you, Ivan, for your questions, very nice questions. So the first thing I would like to say is regarding your first question. So one thing that maybe was not strongly stressed in João's presentation is that we have to assume, when we do a computation like that, we have to assume a state, an initial state for the field. So let's not make it too complex, adding a cosmological constant, not to add, I mean, extra. But let us think about a charge orbiting a Schwarzschild black hole, for instance. It's very simple, zero cosmological constant and everything. So one possibility is to start with a Bower vacuum. An observer at rest outside the black hole sees no particle, right? I mean, and that's what we call, that's what we compute in the beginning. So we start with the Bower vacuum as the initial state. But we could start with Hawking radiation, you see? But this is a kind of initial condition that that you set to your problem. In the particular case of the Schwarzschild black hole, for instance, if you are interested in the net radiation emitted, the result is the same. Because, I mean, you're going to have the Hawking radiation coming from the black hole, but then you're going to have a stimulated emission due to that radiation also. So what we are essentially computing is the net radiation emitted. And in this particular case that I mentioned of Schwarzschild, it doesn't depend, it's just the net radiation is the same. But obviously you can complicate more and more the situation, right? And then just, I mean, to add this comment to your question. And regarding the second question you made, I think João already made, sometimes the words we use are not the appropriate one when saying strongly depends. Obviously, theoretically, strongly depends, right? I mean, if you have an arbitrary large cosmological constant, you're going to have a substantially different result. But we know that that's not the case, but João already answered it properly. Thank you very much. That's what I would like to add.
Thank you, wonderful, thank you.
So I also had this question that Ivan was asking, the second one. So I guess that the strong dependence would happen whenever the Sitter radius approaches the source, I guess, right, or something like that.
Yeah, it's in the context of very high black holes in the context of anti-de Sitter spacetimes.
I have a question regarding this this debate, but maybe I misunderstood. But the thing is, if power is a measure for infinity, then of course boundary conditions that is the cosmological constant is important. Therefore, it makes a difference. But I don't know. Therefore, I don't know if I misunderstood. But if power is measured, although it is emitted from near the black hole horizon, if it is measured for infinity, then of course the cosmological constant plays a role. But I don't know if I misunderstood. Could you please talk about this in a little bit more detail?
I think I did not understand very well the question because my audio at least is very.
Where's the microphone? Okay. No, I was saying that maybe the fact that the cosmological constant plays a role in the calculations, an important role, is because I don't know if I misunderstood what you were saying, but as far as I know, maybe it is because the power emitted by the source is measured from infinity, and then if you measure that power from infinity, then of course the boundary conditions play a role. That is the cosmological constant. I don't know if I misunderstood that, and this is the question.
In this case, the power emitted by the source will be observed at infinity, but at least in in asymptotically flat space times, it can be readily obtained by considering only the in and up modes. But in space-times that have a contribution of the metric at infinity, and this is not easy to calculate, I think.
I think Luis wants to add something.
Yeah. Okay, so what I would like to add, so I don't know the name of the person that made the question, but anyway, thank you for the question. You have guessed correctly. I mean, so what João exhibits is the power emitted, right? And then you have to think about the person that is observing this power, right? And then you have to think about which are the natural observers associated to that. So to which observer the proper time is t, right? And that's why, for instance, when João Paulo says that you are in an asymptotically flat space-time, then for this observer, so the natural time is t, right? I mean, the proper time is t. And then if you think about the falling observer, if you think about different observers, and obviously you have to take into account the transformation to this observer that will lead to further consequences, right? And so, as for each of these, so the zeta, anti-the zeta, so you have to think about which is the observer that has t associated to it, and then if you want to see, if you want to answer with respect to another observer, even the emitted power, then you have to consider the proper transformation. But it's an interesting question. Thank you for asking that.
Okay. Thank you, Liz, for the reply. So, are there any other questions? If not, maybe let's thank João again for the nice presentation. And it's time to introduce the last speaker of today, Abhishek Dusoye from University of Cape Town in South Africa. And the talk will be about constraining Dysformal couplings with redshift space distortion. So please, Abhishek, are you there? I think you're already presenter, like you have like presentator rights, but I am not sure. Abhishek, can you hear us, or can you say something? Okay. Well, maybe it's a bit. Can you speak?
You have to press your microphone. You are in listen mode, only listen mode. You have to refresh the.
I think so. I don't know if the others, but I cannot hear you.
I don't either.
Can you hear me now? Is that fine?
Okay, now.
Okay. So share screen. Now. So can you see my screen?
Yes.
Okay. So you can see me as well, and you can hear me as well.
Exactly.
And my screen.
Yes.
Okay. It's been a long day, so just bear with me for the rest of the talk. Hi, my name is Abhishek Dusoye. I'm a PhD student at the University of Cape Town. Right now I'm in Mauritius, so the time difference is quite a lot. So today I will be talking about constraining Dysformal couplings with redshift space distortion. The paper I'm working has been submitted to arXiv. If you want the reference, it's here. So just an overview of the topic. So firstly, I want to say that this work is a continuation of the first paper we had in my PhD, which was about Dysformal coupling in Lambda Cdm Background. So essentially, what we were considering is a Dysformally coupled quintessence that is mimicking Lambda Cdm. And why we do that is because Lambda Cdm, as we know, is successful observationally, but yet cannot explain two things: the nature of the cosmological constant, which is driving the cosmological acceleration, and secondly, the Hubble tension. But with this model, it's like we are mimicking the Lambda Cdm, yet we have additional degrees of freedom to try address these two issues. So in the first paper, what we did was mostly the background analysis. So in this paper, in this work, the novelty is the treatment of perturbation for this model. And we try to constrain those Dysformal coupling with data. So I will revisit through that, and I just wanted to go through the motivation. So this is a summary of what I will be talking. So there are 5 things, among which the 1, 2, 3 is a revisiting of the background. The first assumption is the Dysformal transformation. So as John Wheeler have said, matter tells space-time how to curve, and space-time tells matter how to move. So essentially, in that concept, the geometry is one. But in modified theories of gravity, such as scalar tensor theories, you find that this geometry doesn't have to be singular. It can be dual, in the sense that there can be a geometry that describe how curvature is, and a geometry which will describe how matter will propagate, and both are connected through the conformal relation. And in GR, the conformal coefficient is 1. So this is in literature, but for this formal,
I think you have something in your screen that says that you're sharing. Yeah, maybe you can.
Oh, I can move that. Okay. Yeah. Okay, cool. Thanks. So for Dysformal transformation is a further extension of this transformation. So essentially, in addition to rescaling the length of the original metric, now we have distortion of angles. This was proposed by Birkenstein. It's also from literature, and in addition to the conformal coefficient, now we have the Dysformal coefficient. So that was the first assumption of the model. The second assumption is that the model is mimicking Lambda Cdm. So what does that mean? On one side, we have the coupled quintessence model, which consists of a scalar field and of a coupled fluid. In this case, we're considering coupled cold dark matter, and they're both interacting. And on the background, we have the cosmological constant, which is also together with cold dark matter. So the construct of the model is as follows. The Lagrangian action is like this, and you have a kinetic part and a potential. Assuming FLRW metric, we can find the Friedman and Ricciardi equation. Variation of the action with respect to the scalar field will give you the modified Klein-Gordon equation, where this Q is what we are referring as the coupling. And in the Dysformal framework, the coupling is described as so. You will notice that I've put references everywhere. If ever you're interested in references, there's a page where I will get back to you. So the conservation equation of the scalar field and the coupled fluid goes as follows. That is, there is a flow of energy momentum from one fluid to the other. And projecting the conservation equation alongside a co-moving observer, we can obtain the following form for the scalar field and the cold dark matter, coupled cold dark matter. So, and then let's look at the Lambda Cdm background very briefly and what I mean by mimicking. So as we know, the Friedman and Ricciardi equation for Lambda Cdm, very simple, it's those two. But what I mean by equating the two cosmological background is literally equating the Friedman equation and the Ricciardi equation. This allows us to obtain the energy density and pressure of the scalar field in terms of the energy density of the cosmological constant. With some manipulation, we'll find that we don't have to specify the quintessential potential because of this mimicry. And so this was the second assumption of the model, of the dysformally coupled quintessence model. Now, what I will describe is more a brief, the result that we obtained in the first paper. It's just a quick revisit and also to get the foundation for the work that I'm presenting. So we have seen the continuity equation. By defining the dynamical variable x, y, z, and sigma, we can plug that into the continuity equation and obtain the dynamical system of first ODE equation. And finally, to close the system, we do specify the conformal and dysformal coefficient. I also want to draw your attention on M here, which is the quintessential mass. It's one of the free parameters of the model. So you have alpha, which is a free parameter, beta, which is a free parameter, and mass as well. Right. So the dynamical system can yield two types of solution, fixed points and trajectories. So the fixed points are static solution where x prime, z prime, and sigma prime are 0. So basically, yeah, I will come to that. And trajectories are non-static solution where the dynamical system can actually evolve from one point to the other. So in this figure, as you can see, this is the conformal solution where the dysformal coefficient is 0. So basically, sigma is also 0. And what is left is mostly x and z, so it's a 2D phase portrait. And what you find, A naught is a global attractor, and C minus and C plus are two saddle points. This was conformal solution, but we can also do the same for dysformal solution. And then sigma is bring an extra dimension to the phase portrait. So now we have a 3D phase portrait. So you can see the XZ plane is a conformal invariant submanifold here down. But I'm not going to detail this because it's already in this paper, but my focus is more on the perturbation for today. So what we also did was we computed the expansion history of the model for fixed alpha and beta. And what we noticed is that, firstly, the features of Lambda Cdm were reproduced as expected with the radiation matter transition and the dark matter dark energy transition being reproduced. We also noticed that the different mass scales affects the evolution density of the quintessence. Lastly, I would say the energy density of the quintessence traces that of a cosmological constant when a low mass scale is utilized. So basically almost flat, like a constant, almost, when you use a smaller mass. All right, so that was basically the background study, but now we'll move forward to the perturbative cosmology. All right. So in addition to what we've seen, the dynamical system being evolved, one can also consider scalar perturbation in the Newtonian gauge along the FLRW metric, and the energy density and pressure of the fluids, as well as the scalar field, is perturbed. So from this you can define the density contrast as so, and the perturb co-moving velocity like this. So since we have modified since we have perturbed space-time, the Einstein equation also will be perturbed for the coupled quintessence model, where these two equations are like the modified Poisson equation, and the last equation is the evolution of the potential. And you can see the source term appearing here. And you can see the scalar field also source in those equations. I will also mention that C denotes cold dark matter, and B denotes the baryon. Right. We've seen the continuity equation a moment ago. Now this is the perturbed continuity equation for the scalar field, this one, and this is for the dysformally coupled dark matter. I want to also draw your attention on Q1, where now we have perturbed the interaction, we have perturbed the coupling, Q1. In literature, you will find the perturbed interaction term to be something like this. So from this point, I won't get into detail in terms of the mathematics, because it's quite rigorous. But I will come down to say that after some derivation, you can obtain the second order differential equation for the baryonic density perturbation also, and the second order differential equation for the density perturbation of the cold dark matter, which is dysformally coupled to quintessence. We have also used some we have renormalized some variable for simplicity. So Q naught is the interaction term, Q1 is the perturbed interaction term, and then Q naught prime is the derivative of the interaction term, and Q1 is the derivative of the perturbed interaction term. So So the prime is like the derivative, and then this and this. Right. Now I'm just gonna show some of the results we obtained for analyzing those. Actually, I want to mention. So these two evolution ODEs were coupled together because you can see there is a delta density contrast for baryon here, which appears here, and then the density contrast of cold dark matter, which is evolving and appearing here. So they are coupled. So as we are solving them numerically, it's a coupled system, and at the same time we have to solve the background altogether. So in the result, what we are going to see is, so I'm showing you the evolution of the total matter perturbation, dt, delta t, and it's defined as this, where z square was one of the dynamical variable that we defined. I also want to mention that we analyzed the effect of the quintessential mass m on this rate of evolution, and we found that there is a relative difference between lambda CDM. So the black line is the lambda CDM, the solid line are conformal, and so in terms of colors, the green lines correspond to the conformal case with alpha is 0.05, and the orange line correspond to alpha is 0.08. And what I want to show you is the dashed and dotted. The dash and dotted correspond to the effect of the quintessential mass. So basically, the dash is m is 200 MeV, and the dotted is 100 MeV. Apologies, this is small MeV. It's a typo here. It's milli electron volt. It's a typo. Apologies. And also, the next part of the analysis was to investigate the effect of the quintessential mass on the growth of the large-scale structure. So again, what we did is having the solution for the delta t, and we can hence find f and then f sigma 8 through those definitions. So and then we plotted f sigma 8, right? So the black line is lambda CDM. The solid lines are conformal, purely conformal, and the dash and dotted correspond to, again, the two values of m. For easiness, we have redefined m as dm. So dm is the inverse of the mass scale. We have also made a chi-square estimation against the Rsd data. So basically, from here itself, you can see the solid green line, which is conformal, and like with a high mass, so smaller dm, higher mass, is favored because it has the lowest chi-square. All right, so I think I will move, okay, so based on those two figures, there are some remarks, is that we recover lambda CDM as expected. So for non-zeros values of alpha and beta, the conformal nature of the dominates at low values of dm, that is high mass. And this formal framework is more significant at higher values of dm, so lower mass. This was shown in the first paper. We find that the model behaves conformally. So basically, we have reproduced the results of conformal. So the solid lines here were results that was already produced by Barros et al. This reference. Okay. So we were able to reproduce that, and then we can see that for the for a fixed choice of alpha, the parameter dm induces a gradual dysformal effect. Also, so this effect means that the rate of evolution delta t is increasing, leading to higher values of f sigma 8 relative to its conformal case, meaning that the structures cluster faster when compared to its respective conformal cases. And lastly, what we did is a Bayesian analysis of the free parameters. So we have 4 free parameters, sigma naught, actually it should be sigma 8 naught, it's unrevertible, sorry. The current value of sigma 8. And you have alpha, beta, and dm. So what we did is we investigated like a multidimensional parameter space where every grid point we can find the likelihood function. Firstly, what we found that beta was marginalized out because it appears to be degenerate. No matter what value of beta, we found that the likelihood is like a constant, so it's not contributing to to any effect. So in this figure, what we find is that it's like the marginalized. Sorry, it's the surface likelihood shown in top view where we have marginalized one parameter, and then we have marginalized 2 parameters. Right. In the green region, we find the confidence region of 68% and the blue region with 95% confidence. The best fit was found to be 0.8, 0.08, and DM is 0.001. What that means is the Rsd data is favoring like a low numerical value of dm. So basically, it's favoring when the mass is high. So so basically, this formal coefficient literally dies off. It prefers mostly like conformal. It prefers the model when it behaves conformally. Those results that we found, sigma naught, alpha, and dm, sigma naught and alpha was also obtained by Barros in their own Bayesian analysis. So it's kind of saying it's a negative result in the sense that it prefers the model to behave conformally, despite we've put a lot of effort investigating the dysformal framework. I think that will be it. So if you have any question, so thank you very much.
Okay. Well, Abhishek, for the talk. So any questions from the audience? Okay. If not, I would like to ask, there were some couplings between the scalar field and the stress energy tensor that you were showing.
Yes.
So first of all, do you know if these kind of models are constrained by propagation speed of gravitational waves? Because I remember that there's like a large class of constraint of theories, which I think includes these formally like these formal couplings and stuff like that, which are like severely constrained by gravitational wave observations from the joint effects of gravitational and electromagnetic propagation, but I am not sure about these ones.
I think firstly the model is quite specific because it's there are a lot of model for like Dysformal coupled quintessence model in literature, but this one specifically mimics Lambda Cdm. I'm not sure if there were. So I've been working with Nelson, Professor Nelson Nunes. He only once told me that the gravitational wave analysis is like there's nothing promising there, but I'm not too sure. This is what he told me. So, but it's worth rechecking if there could be some work done there as well.
Okay, and also I was commenting about the couplings to the stress energy tensor because I found similar couplings in other models that I was studying, and I managed to constrain the coupling constants, or maybe in this case the mass of the Dysformal transformation, by considering scattering experiments in accelerator physics. So maybe it works for you. I don't know. I mean, it was just like something. We can talk about that if you want, like by email or something.
I think Carsten also did well, we can talk about that. He did some constraint as well with I'm not remembering. Like Professor Carsten van de Broek, he did some work about constraining cosmological constant with this formal coupling. But sure, we can chat about that. Sure.
Okay, yeah. Let me know. Like, just send me an email and I can like explain. So, any other question in the audience, or maybe it's time to.
Yeah, it's been a long day.
Okay. So let's thank Abhishek again, and I think I am in charge of closing the meeting, right? Or Gonzalo is already there? No. Yeah, I should close it. Okay, so thank you everyone for coming to this new edition of the Winter Workshop, which now is kind of mixed between virtual and present talks. So we'll start tomorrow again at 10 with the talk by Florencia, and I hope to see you all there. So thank you very much, and have a nice evening or night if it's too late at your place. Bye.
Bye.
Bye.